In early 2024, the Gaia mission noticed something strange just 2,000 light-years away, practically next door on a galactic scale. A stellar mass black hole was hiding in plain sight, but this was no ordinary black hole. This black hole weighs 33 times the mass of our Sun. It is the heaviest stellar black hole ever discovered in the Milky Way. It was named Gaia BH3. And technically, it shouldn't be here. Black holes of this mass usually form in low metallicity environments, places where the recycled matter of exploded stars didn't exist yet. In other words, in the early universe. Yet Gaia BH3 is just quietly orbiting a dying star as if nothing happened. No accretion disk, no X-ray fireworks or warnings. It's like finding a dinosaur drinking from a puddle in your backyard. So either our models of stellar death are more flexible than we thought, or something from the deep past managed to slip through the cracks and survive. This isn't just a cosmic oddity. It feels like a message. The universe isn't quite what we thought it was, according to our fancy theories. I've noticed that lately, the astronomical world has been full of exactly this kind of news, from the good old solar system to distant galaxies and the behavior of the universe itself. Here are the freshest, unexpected discoveries that challenge our understanding of the cosmos. For decades, Mars was the poster child for planetary disappointment. Once hailed as Earth's twin, it turned out to be a red, cracked marble, a place where there was once water and hope for a great future. We thought everything about Mars was clear. It's dead, dry, and geologically quiet for billions of years. But that's not the case. In 2024, a series of radar scans and seismic measurements from the InSight lander and orbital spacecraft began whispering a different story. Beneath the surface of Mars, under layers of regolith stretching for kilometers, hides something incredible. New data points to massive underground reservoirs. You guessed it, most likely they contain water. Entire oceans that seeped down through the upper crust when it dried out. And this changes everything. If water truly exists there, even entombed under rock and ice, then Mars maintained internal activity much later than we thought. This could mean conditions stable enough to preserve microbial life for millions of years, and not just in the past, but right up to now. Although it is worth noting the skepticism of some scientists who point to the oceans being filled not with water but with liquid carbon dioxide. This is bad news for potential life. But in any case, it means Mars is not the barren, fossilized world we imagined. And while we still don't know exactly what's inside, this discovery has shaken the foundations of our understanding of planetary life cycles. Thousands of exoplanets orbit stars, and we have only just begun to study them. We classify them by atmospheric composition, temperature, position, but what if our categories are built on false assumptions? What if other dead worlds are quietly hiding oceans of possibility beneath their surfaces? And if a frozen planet nearby might store the ingredients for life, then what can be said about other corners of the universe? In 2025, astrophysicist Daniel Whalen and his team proposed something that flips cosmic chronology on its head. According to their simulations, planetary building blocks, rocky planets, could have formed as early as 200 million years after the Big Bang, and this inevitably means conditions for liquid water on their surfaces, at least in some places. Imagine, for cosmic standards, the first rocky planets like Earth appeared literally moments after the universe cooled enough for atoms to form. This is much, much earlier than anyone expected. We're talking about hundreds of millions of years of difference. Until now, we believed that rocky planets appeared at a late stage of the universe, as they supposedly required several generations of stars to create heavy elements for their cores and crusts. But Whalen's work suggests that these materials were sufficient even in the ashes of the first stars, and all this raw material formed into worlds capable of supporting life, at least microorganisms. And another recent discovery only adds to the probability that conditions for life in the universe appeared extremely early. The James Webb Space Telescope helped astronomers studying the oldest and distant galaxies to see in one of them, Jade's GS Z14-0, something that shouldn't have been there. Oxygen, lots of oxygen. This means that this galaxy, which we see as it was only 300 million years after the Big Bang, had already survived at least one full cycle of star birth and death, and this shifts the appearance of complex chemistry to a significantly earlier era of the universe's existence than our models predicted. And this leads to a depressing realization. If planets could form so early, and if the elements needed for life were already scattered across the universe, perhaps life wasn't waiting for us. Perhaps we're not the first, but just another chapter in an ancient book. But this inevitably reminds us of the classic Fermi paradox. Where are all those aliens who could have appeared 13.5 billion years ago, almost immediately after the Big Bang? In all that incredible time, they could have colonized the entire observable universe 5 times over. So what killed them at the very beginning? Perhaps I have found the answer to this question, and it is chilling. Ever since the first images started coming in from James Webb, astronomers have repeatedly noticed these things, tiny dots scattered across deep space images. At first, they seemed rare and inconspicuous, but they appeared again and again, literally in the hundreds. These objects were christened little red dots, but this innocent name is misleading, considering that here we might be dealing with the most disturbing discovery in modern astronomy, because these objects are not galaxies, or at least not the galaxies we know. Astronomers estimate their size at 150 to 500 light-years in diameter. That is, these objects are so tiny that you would hardly notice them against the backdrop of our Milky Way. But that's only if the little red dots weren't so incredibly bright. The first suspects were quasars, supermassive black holes in the process of devouring matter. There were plenty of them after the Big Bang, but the little red dots don't glow like a typical quasar. They seem to lack X-rays. What if they're just tiny proto-galaxies with incredibly bright stars? No, that's nonsense too, because what are the chances of seeing hundreds of such identical anomalous star balls around us? According to modern models, little red dots simply shouldn't exist, and yet they are here. Or rather, they were here, as they completely vanished after the first billion years of the universe's existence. Spooky. Perhaps those very things somehow killed all early life, which is why it developed much later. The latest research hints that little red dots are actually an unusual type of quasar. We are seeing an incredibly dense cocoon of gas and dust hiding a feeding supermassive black hole. This explains the absorption of X-rays, but it doesn't answer the question of how and why such cocoons suddenly formed everywhere and then disappeared. So let's not pretend it's business as usual and admit our models of the early universe are built on sand. It is time to start digging even deeper, because just as astronomers began to suspect that these tiny dots might be obscured quasars, one of them pulled a stunt that was completely unbelievable. The object JADES GS-Z13-1 seems like an ordinary little red dot. It is one of the brightest and earliest compact galaxies discovered by James Webb. The problem lies in its light, specifically Lyman alpha radiation. This is the name for a wavelength of ultraviolet light usually produced by young, hot stars. Under normal circumstances, this wouldn't be strange, except that at the time this galaxy existed, only a few 100 million years after the Big Bang, the universe was not transparent like it is today. It was then still filled with neutral hydrogen, a thick cosmic fog that absorbed and scattered exactly this kind of light. Therefore, according to our models, no Lyman alpha radiation should have flown through it. It should have been absorbed by the hydrogen haze of the early cosmos. We see this same effect, the so-called Lyman break, in all galaxies of that period. But this little red dot seems to ignore this and cuts through the cosmos with ultraviolet light as if the fog never existed. This destroys one of the central ideas of modern cosmology, the epoch of reionization, the moment when the universe went from opaque to transparent. We thought this happened gradually over hundreds of millions of years as the first stars and galaxies ionized the fog and their light broke through it. But if galaxies like JADES GS-Z13-1 had already broken this barrier, then either reionization began much earlier than we thought, or it happened completely chaotically. Perhaps the process of the universe gaining transparency didn't look like the slow lifting of a curtain on a stage. Perhaps it cleared in fragments, violently, disorderly, like a spotlight cutting through clouds in a storm. But what makes intuitive sense to us is a nightmare for cosmologists, who will now have to rework their models for a chaotic reionization. The next discovery shook the foundations even harder, this time of space itself and how it evolves. In 2025, researchers working with DESI, the Dark Energy Spectroscopic Instrument, published the largest 3D map of our universe. But here's the surprise. As this data shows, dark energy, the mysterious force accelerating the expansion of the universe, is not at all what we thought it was. Since the late 90s, we have been guided by the simple but elegant idea that Einstein's cosmological constant, lambda in his equations, represents a fixed density of energy in the vacuum of space. Simply put, a constant cosmic pressure that gradually pushes galaxies apart. But the DESI team noticed something strange in the distribution of galaxy clusters at great distances. Their pattern doesn't quite match predictions. This relates to so-called baryonic oscillations. They're effectively ancient cosmic sound waves that led to specific clustering of matter. Because of this, we see more galaxies at the peaks of former waves. But when the DESI team examined the data, these galactic rings turned out to be larger than anyone expected. And this inevitably means that in those times, dark energy would have been noticeably stronger. If this is true, then lambda is not constant as we thought, and our convenient lambda CDM model, the cornerstone of modern cosmology, is ruined. It is built on an unchanging component of dark energy to explain the formation of the universe. So what is happening? One possibility, dark energy is actually not a static force, but a dynamic field, something fluid and changing, like cosmic weather. Theoretical physicists call this idea quintessence. It is a scalar field with certain fluctuations that affect the rate of the universe's expansion by changing its state. Another possibility is even more radical. Perhaps vacuum energy is unstable. That is, space itself has phases, like water turning into steam when heated, and we are simply observing this slow transition. In any case, we have entered a realm that standard physics cannot yet describe. Our equations will require a total overhaul, if, of course, the DESI results are independently confirmed several times. The positive side is that with the weakening of dark energy, the universe will not undergo a big rip, where even stars and planets would be torn apart by the expansion of space. Perhaps the cosmos will eventually contract to its original form and cause another Big Bang. But I'm getting ahead of myself. I suggest we just wait 1 trillion or 2 years and see everything with our own eyes. Meanwhile, another discovery is quietly pulling the rug out from under any ideas about how the universe should behave. In 2025, astrophysicist Lior Shamir released a study based on data from the James Webb Telescope's Advanced Deep Extragalactic Survey. And what he found challenges one of cosmology's most sacred assumptions: the entire universe might be rotating. Shamir analyzed over 260 ancient spiral galaxies, focusing on the orientation of their spin, clockwise or counterclockwise from our point of view. In an isotropic universe, meaning one without any preferred direction, the distribution should be roughly equal, half clockwise, half counterclockwise. But that's not what Shamir saw. Instead, about 2/3 of his galaxies rotate clockwise and only 1/3 counterclockwise. And this isn't a small discrepancy. The asymmetry is so strong that it suggests one thing: something forced these galaxies to choose one direction over another, as if there is a global axis of rotation for the observable universe. Or, simply put, it is spinning. And this is a huge deal, because this rotation shatters the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. This is the cornerstone of modern cosmology. No place and no direction should be special. Moreover, a rotating universe would twist the very fabric of space-time. This could cause distortions in how light travels, in how galaxies drift, and even in the flow of time. It's a possibility we never seriously considered because we thought it simply couldn't be. But here's the surprise. This global cosmic rotation might help us explain the variability of dark energy I mentioned earlier. Data from projects like DESI could have been distorted by the subtle motion of the universe itself. Hence, the illusion of unstable dark energy appeared. So it's a radical idea, but it's already starting to win supporters. Perhaps the universe has been spinning from the very beginning, just like our Earth. We just didn't notice it. But the real question then is, what made the entire cosmos spin? If Lior Shamir's results are confirmed, the simplest explanation would be this: we all live inside a black hole. This theory is called black hole cosmology. For decades, we considered it just a cute, paradoxical idea. You see, if you compress all the matter of the observable universe into a single black hole, it would be almost the exact same size as the observable universe. Funny coincidence, isn't it? Perhaps we should take this idea more seriously, considering that all black holes we know of rotate, and evidently our universe does too, even if very slowly. So, write in the comments how you like the interior of the largest black hole in the universe, and also tell me which of these discoveries impressed you the most. Stay with me, because the universe seems to have only just started testing our ideas about it.